Hey kids, Charlie Abuso here. We are, am I recording? I don't even know. Let me try this again. Breakout room, stop recording, pause. No, I guess I'm recording. Here we go. Question 32 from the notes. We have nitric acid and magnesium hydroxide. They are on tables K and L. And if we write the formulas for the nitric acid and the magnesium hydroxide, we see very quickly that this is what they look like, HNO3. Magnesium hydroxide is a double hydroxide because magnesium is a positive 2 ion. Now they're going to turn into a salt and water. Now the arrows up above are a little funky because, well, they are. That salt arrow is still pointing to magnesium hydroxide. I should make that sentence on the top a little bit smaller, but I can't. The H and the OH in red on the bottom, they're going to turn into water. And the magnesium and the nitrate are going to go together in a 1-to-2 ratio because the magnesium is a positive 2 and the nitrate is a negative 1. And then this is the balanced equation. Magnesium nitrate, positive 2, negative 1, so it's a 1-to-2 ratio. And we're going to need to make 2 waters because it's a double hydroxide, so we need 2 nitric acids. And that gives us 2 hydrogen ions and also gives us 2 nitrates. So it works out fine. This is a simple balanced chemical equation. Hopefully you're going to be able to do stuff like that on your own. We got a couple more coming up in this class. Now, we're going to get through the alternate theory of explaining how ammonia is a base, and we're going to also do some more practice, but we're not going to get to the pH or the acid-base chemicals until tomorrow. All right, 99% of all acids and bases are Arrhenius acids or Arrhenius bases. They have hydrogen ions or they have hydroxide ions to be acid or base, and when they combine, they form salt and water. But ammonia is a weak base, and it does not follow the Arrhenius theory. It has no hydroxides. The formula is NH3. We have what's called an alternate theory. It has a name. You don't have to worry about that. The alternate theory, it defines ammonia as the base because of how it acts. Now, what's on this next slide is also in the flashcards. You must absolutely memorize this. It's that important. So this is what we have. Ammonia, which is a gas normally. It's a very small molecule it's a gas and boils at a very low temperature, like crazy cold. It's just a gas. When it goes into liquid water, this is what happens. Now, only about 25% of the ammonia is going to do this. Probably 75% of the ammonia just dissolves because it's a polar molecule. But about 25% of it is going to do this. The ammonia is going to accept a hydrogen ion. Now, where did that hydrogen ion come from? Now, the water, HOH, we write it like that in acid-base chem. The H in the front is going to break free. The water is going to donate that hydrogen ion. So ammonia, which has 3 hydrogens, is going to gain, not really a hydrogen, it's going to gain a hydrogen ion from the water. It becomes, instead of NH3, NH4, but it's not really NH4, it's NH4 minus an electron. So it's really the NH3 gains the hydrogen ion. And then the leftover part of water, the water donated that hydrogen ion and the OH hydroxide shows up in solution. Now, when you put ammonia into water, 75% of the ammonia just dissolves because it's a polar molecule. But about 25% of it is able to kind of bust open the water, and ammonia becomes ammonium. And water, when it donates that hydrogen ion, it becomes hydroxide. Now, Mr. Arrhenius gets the Nobel Prize because he said hydroxides in solution cause the base properties, and the hydroxide is what gets neutralized with the hydrogen ions. These guys came up with this alternate theory to say, wait a second, let's not, who cares about that hydroxide at the end? We want to get a Nobel Prize, give us the notoriety. We'll say instead of, oh, look what happens when you put ammonia in water, hydroxides show up. No, we're not going to talk about that. We're going to say ammonia is a base because it can accept a hydrogen ion, and then crazily, to keep their theory, we have to now say that water is an acid because it donated a hydrogen ion. Now, we all know that water is neutral. Water is not an acid. This is a wacko theory in some ways. What they should have said was, oh, wow, when you put ammonia in water, hydroxides come out of it. And that's why it's a base. But they didn't want that. They wanted to selfishly get their own credit. And they said, no, it's not the hydroxides. We'll say that the ammonia is the base because it accepts a hydrogen ion. And at the same time, water has to be an acid because it donated the hydrogen ion. So it's a crazy theory, but this is what happens. Hydroxides show up. That's why it's a base. That's what gets neutralized. That's why it feels a little slippery in your fingers and it's not wet. It's a base because there's hydroxides. But officially, according to this theory, ammonia is the base. So you kind of have to memorize that, and I'm sorry. Now, we're going to do 3 of these in a row, and we'll be done. Carbonic acid and lithium hydroxide are going to make a salt and water. Okay, or water and a salt. Either way, I don't remember how I wrote these, but I like salt and water. These should be salt and water. Carbonic acid has 2 formulas. We're going to use the big one with the H. H2CO3, and lithium hydroxide is actually not even on table L, but lithium hydroxide is LiOH. So we're going to set this up, and wow, I have to figure out a way to make these slides a little better for you guys at home. The carbonic acid and the lithium hydroxide are going to make water and lithium carbonate. So this is the balanced chemical equation. It could be lithium carbonate and water, and I'm going to fix these so that they work, but that's not how it's going to go. Now, this next slide also, the products are water and calcium acetate. So acetic acid has this formula. We're going to use the bottom one. The top one is the organic formula. We use the bottom formula. And calcium hydroxide is on table K, table L. It's a base. It's going to make water and calcium acetate. So if we do this, we're going to have C2H3O2 and calcium hydroxide. It's going to turn into 2 waters and calcium acetate. The last one, phosphoric acid and sodium hydroxide. Phosphoric acid is the one with the H3PO4. That's in table K. Sodium hydroxide is the strongest base. It's going to make water and sodium phosphate. And once you balance this, which you should be able to do, I'm going to show you the answer right now, is this. Now, again, I usually put salt and water. I don't know what I did on this slide. It's water and salt, but it works the same way. Salt and water, water and salt, it's salty water. Either way. And I believe that this is the end of this show. Yep, we're not going to talk really about this next slide. The acid-base indicators are chemicals like this one, phenolphthalein. We're going to see this tomorrow. Or another one could be called, this one is bromethymol blue. These are different chemicals that will change color, whether there's acid or base, but there we go. That is this short class. Please check the website. There's some stuff you owe me that's old, and I have reminded you about that. We're going to get through all of the acid-base notes, and we have the acid-base color chase, the pandemic acid-base color chase lab. We'll be using the indicators coming up this week, and then we're going to do the titration classwork and the titration, pandemic titration lab next week as well. Acid-base is wonderful. All right, good day. Bye-bye. See ya.